Hello, everybody. My name is Makarov Evgeny. I work as developer technology engineer at NVIDIA. And today with Chae-Woong Cho, we're going to present to you our talk regarding creating next-gen agents for upcoming game inZOI from KRAFTON. Please welcome Chae-Woong Cho. He works in deep learning department at KRAFTON, and this is his first GDC. Please welcome him. And he's gonna share a lot of cool insights, really lots of technical things, lots of things you will learn and hopefully like from this talk. Please welcome.
Thank you. Good morning, everyone. I'm excited to share the work we work with NVIDIA. And as everybody gave the introduction, I'm a deep learning researcher at KRAFTON. And I'm going to show what we do today, creating next generation agents in KRAFTON. Let's get started. So inZOI is a new life simulation game developed by KRAFTON using Unreal Engine 5. And in inZOI, you will step into an open world where realistic characters live and interact based on their free will and unique personalities. So in this open world, you can make deep relationships, find a job, have a family, or even get conflict, just like in the real world. And you can change any aspect of the world, creating your own unique story and experience in the game. So the early access version is going to be released on March 28th. So we hope you to enjoy the game. All right. So the ultimate goal of this game is to provide users an immersive experience of living the life they've always dreamed of. So to achieve this, our simulation focuses on three key focus. So the first key feature is realistic graphics. We focus on high-quality visuals to make the game's world and character feel as natural and immersive as possible. And the second feature we focus is world and character customization. inZOI offers a variety of creative tools, allowing users fully customize their character's appearance and shape their own world, and every detail can be tailored to their preferences. And our third focus is SmartJoy, which drives characters' behavior and reasoning. And this is SmartJoy is the key focus of today's presentation. SmartJoy is a language model-based life simulation engine, and we are completely redesigning life simulation games, and inZOI is the first one that can run entirely on a language model-based engine. And with SmartJoy, we're not just replicating what traditional engines do, we are introducing new features made possible by a language model. So SmartJoy can plan their day, make decisions based on its schedule and surroundings, and even write free-form diary, all without prescripted content. And adding to these features, now you can customize not just the world and character's appearance, but also characters' action, thoughts, and relationships, all through natural language. If we just describe it with the text, then the game will understand it. So inZOI feels natural than traditional life simulation games because story evolves dynamically and making every experience unique and immersive. That's the SmartJoy. So in this talk, I will give answers to these two key questions about SmartJoy. So the first question is, why do we need a language model-based engine? And the second question is, how did we design and build our language model-based engine?
Yes.
So let's start with the first one. To answer the first question, we will first look at the previous approach of modeling behavior and its limitations. A traditional method, utility AI, is a simple yet efficient way to modeling decision making, and it works by assigning the score to the possible actions based on the current game state and select the action with the highest score for choosing the best action. That's a utility AI. Then how to design utility AI in a life simulation game? To build a utility AI system, we first need to define and model the game state. And one common approach in a life simulation game is need-based modeling. For example, we can define 8 types of needs, such as hunger, hygiene, sleep, bathroom, and more. And each need is represented on a number scaled from a negative 100 to 100, for example. And where higher value means the need is well satisfied, and the lower value is for urgency. And the value decreases over time at different rates, depending on various factors. For instance, if character drinks water, then bathroom value will decrease fast. And once we have a structured game state, then we need to assign scores to each possible action, representing how much this action impacts a specific need. In this example, eating action might increase hunger by +7, while watching TV increase fun need by +5. Then what's the next step? Let's see. Then we use weight to adjust priorities of actions based on the character's current state. A designer model the value of weights as a function of needs, and then by multiplying the weights with the action scores, we calculate a final utility score for each action and select the best one. That's the utility AI. So if a character is extremely hungry, then the weight for hunger-related action has high value, making eating action a much higher priority. And this mirrors how humans make decisions where urgent needs take priority over less important ones. This forms the foundation of basic utility AI in a life simulation game. Right. Then what is the limitation of this manually designed utility AI? If we want to make characters behave in a more human-like and immersive way, they need to consider past experience or more complex contextual factors, not just their immediate need. So let's take an example. A character is hungry at 5:50 p.m., but has a dinner reservation with his fiancée at 6 p.m. A basic utility AI will simply recognize that hunger value is so low and decide to eat something right away, which completely ignoring the fact that the dinner is just 10 minutes away. So this could lead to an unrealistic scenario, breaking immersion. And there is a way to solve this. One way to solve this is by adding a rule. If there's a dinner reservation within 1 hour, don't eat anything. But there's the problem. Real-life decision-making isn't just about 1 or 2 fixed rules. So manually designing rules for every possible scenario is not scalable. The more complex situation we try to handle, the harder it gets to expand and maintain the system. That's the limitation. However, we now have a new opportunity to model complex human behavior in a more natural way. Modern generative models like large language model are trained on diverse data sets that capture real life of humans. As a result, these models understand how people live, communicate, and behave. And this makes them a powerful tool for simulating human-like behavior and interactions. Let's get back to the scenario where character is hungry but has a dinner reservation in 10 minutes. as you can see in the slide, I asked a question to the large language model, OpenAI GPT-4o. You are hungry at 5:50, but you have a dinner reservation at 6. Will you eat the bibimbap right away? Bibimbap is Korean food. Then the model generates a reasonable answer like a human. No, I wouldn't eat bibimbap right away because dinner is only 10 minutes away. And I wouldn't want to ruin my appetite, especially it's a special meal with my fiance. So like the example here, the large language model has capability to understand most of the context and generate reasonable responses. Okay, so with this great opportunity such as large language model to model believable human behavior, researchers have explored a proof of concept for large language model-based generative agents. And I want to introduce a research paper, Generative Agents Interactive Simulacra with Human Behavior, which is conducted by researchers at Stanford University. And this study demonstrates large language model-based generative agents by simulating 25 agents in a small-scale sandbox environment called Smallville. And in this simulation, agents live out their daily lives, making decisions based on various contexts and plans, and developing social behavior through interactions with each other. So this emergent behavior demonstrates a key advantage of large language model-based life simulation engine. They can understand context, adapt dynamically to new information, and generate believable interaction with each other, all without the need for manual role design. That's why we need a language model-based simulation engine in the advanced life simulation game. Okay, so now we are ready to move on to the next question. How did we design and build our language model-based engine? So there were 4 technical challenges to build a smart GDC. One of the biggest challenges was that there was no stable language model-based agent system that could directly apply to inZOI. Almost all agent systems developed in this field was built mainly for research purposes. So it tried to incorporate too many features at once, which made it difficult to be large-scale and production-ready. So inZOI needed an agent system that could function in a large open-world environment, unlike small-scale simulations. So from this, another major challenge was latency. The proof of concept agents relied on multiple large language model inference calls to make a simple action decision, making it hard to achieve real-time decision. But for inZOI, players can operate at 5 times speed gameplay, meaning agents had to make decisions quickly to ensure delay-free gameplay. Also, running large language model-based agents on a server would lead to continuous operational costs. So we didn't want. So to address these issues, we have 2 ideas. First, we designed a new agent system from scratch to make it scalable and production-ready. And second, we built a scalable, fast, and sustainable agent for real-world gameplay using on-device small language model so that we can eliminate continuous server cost. Through combining these 2 ideas, we built a smart GDC. So smart GDC live their daily life doing action selection and inner thought generation. And before going to bed, smart GDC write a diary, then make their daily planning for the next day. Lastly, you can customize characters' behavior and thoughts by entering prompts using the feature that we call Smart GDC Pen. Let's see how it works in the live demo. Okay, this is inZOI, and there are 2 people who are family, Grace and David. So they are husband and wife. there is a toggle that we can turn on and off for Smart Joy. If we turn off Smart Joy, then the character will be moved by utility AI I explained. So we can see the state of each character here, hunger, hygiene, and more. And let's play. If we turn off the Smart Joy, then they make a decision based on utility AI, which assigns scores based on their current state. Okay, what is she doing? Let's see. She's choosing the action, investigating interesting facts, right? And inZOI can play 5 times fast play here. Okay, so we need to make a decision as fast as possible. So there was a latency issue for Smart Joy. So let's turn on Smart Joy now. What happens? Cancel the action. Yeah, if we turn on Smart Joy, then small language model choose the action, what they do, based on their current state and context, and they provide the inner thought regarding their action. Let's see, so small, but the mouse clean and poses feels productive, feels like the resettled what's next. Yeah, they are showing their inner thought about their action, which is clean mouse. So let's see what happened to the David if we... Alright. He chose splash water playfully. And the inner thought says the cool water feels nice. Smooth start the day. What's next? Okay, they show their inner thought regarding their chosen action. Okay. And there is a pen feature. If you click, then you can enter the prompt that you want to customize your character. For example, you love your wife so much. Then the character behave and give inner thought based on this Smart Joy pen feature. And if you give the opposite way, you hate your wife so much, then the action is totally changed, and their inner thought is totally changed based on this prompt. Okay, so that's the Smart Joy pen. And I want to show one more feature. Let's move the time to after 11 p.m. All right. After 11 p.m., I want to make him sleepy. Oh, sorry. Yeah. Okay, there we go.
Let's
see. Let's see what happened. Okay. After 11 p.m. when he's sleepy, he go to bed and generate diary based on his history action of today. So generate diary, then he make a plan based on their reflection. And he totally changed the plan where to go and what to do for the next day. It is not explicitly shown in here, but the made plan is going to the small language model to make a decision tomorrow's action. All right. So Let's move on to slide again. Okay, this is Smart Joy. So all tasks for each joy, including action selection, inner thought, daily reflection, and daily planning. And these all tasks are performed in a 500 million size small language model called Minitron from NVIDIA. And the more important thing that I want to mention is that the small language model is running on user's device together with the game client. Then how do we run all tasks in a single small language model? We can run all inference in a single language model by simply modifying the character-specific information and task instruction in the prompt. For example, Joy 1 is hungry and like meat. Then small language will select eating meat as an action. But if we change this Joy to vegan diet, okay, then small language model will take eating salad as an action. And if we change the task instruction from action selection to daily reflection, then the output will totally different. The model understands the instruction and will generate the diary. Okay. Then you might wonder how we design and build Smart Joy. We had 3 steps of Smart Joy development. First, we have to develop an agent system from scratch, as I mentioned, to build a scalable and production-ready agent system for inZOI. That's the first step. And then we verified that our design system performed well with large language model, but struggled with small language model without fine-tuning. And to address this, we fine-tuned the small language model using data sets collected from the large language model agent. Finally, we optimized and integrated the small language model into the game, ensuring efficient performance. Okay. Let me introduce how we designed the system, overall system. So we start with action selection agent, which make decisions based on the current situation. It can basically make Joy live a day by choosing an action. Building on this simple foundation, we gradually introduced additional features. For example, the first addition was a reasoning generator, which generates the character's inner thought for each selected action. That's the first one. Now, Joy does not just act. It shows the reason of a behavior or their emotions. Next, we added daily reflection agent. This enables Joy to reflect on the day before going to sleep and captures the key moment and thoughts of the day. That's the role of daily reflection. And finally, we introduced the daily planning agent, which takes insights from daily reflection and use them to plan the next day more meaningfully. And by structuring the system this way, we designed a relatively simple yet stable agent framework that allows multiple Joy to live out their days. And we're going to explain each agent step by step from the next slide. Right. So let's start with action selection agents. These agents choose a behavior among possible actions. All possible actions can be categorized into the following 3 categories. First, interaction with an object. And second, interaction with other Joy. And last, self-directed behavior, such as fart secretly. And if we list up all the possible actions, then it is too long. Then it is hard for our language model to understand everything at once. So it's hard to choose a proper behavior for large language model if we list up all actions in that way. So to simplify the action selection process, we divided it into two stages. First, choosing which object to interact with, and the second, selecting the specific interaction for that object. And in addition to this, since latency is affected by generated token lengths from language model, so we optimize the system to return only a single token that represents the action index instead of a wrong response, such as the first line. We choose index B instead of generating wrong answers such as I will choose John. So this adjustment significantly reduces response time, making action selection faster and more efficient. Okay, so this is how object selector and action selector agent works. They use the same language model, but with the different prompts. First, we give this information such as character information, word information, task instruction, plan, object list. Then language model select the index of object to interact with, let's say B, John. Then we feed this output into the action inference prompt where the large language model select the index of the interaction to perform with the chose object. In this case, the action selector will choose greetings. So action will be greetings to John. Okay. So let's see the detail of the prompt in the slide that we use. In our system, we carefully design prompts to ensure the language model understands the task effectively. So to do that, first we include key details such as personal background, status, relationship information, task instruction, your plan. And all information is converted into natural language sentence, making it easier for the language model to process and interpret. And we provide clear and specific guidance in the prompt, such as this. So to help the model execute the task accurately and consistently. So by structuring prompt this way, we ensure that the language model processes context effectively and generates appropriate response for all tasks. Okay, next, let's move on to reasoning generator. Reasoning generator provides the inner thoughts behind the character's actions, helping players better understand their behavior. After an action is decided, it generates an inner thought that reflects the character's logic and emotions. For this agent, and especially, we pay close attention to style instruction of writing so that the language aligns with each character's unique tone. For instance, we give details such as use vocabulary appropriate to your age, or use vivid natural language that reflects personality and avoid repetition or cliché. We give all details to language model generate the well-aligned text for inner thought generation. It is important because it directly impacts the user experience, as it is typically displayed in the inner thought pop-up. And let's move on to daily reflection agent. So daily reflection is performed when go to sleep action is selected after 11 p.m., as we saw in the demo. The system analyzes by comparing the daily plan with the history of actions and then write a diary. So we also carefully design the writing style instructions for the diary, ensuring that each character's diary reflects their unique personality and way of speaking. And lastly, for daily planning, similar to how daily reflection works, we incorporate the result of the daily reflection into the prompt to generate the plan for the next day. And we will skip the detail of planning agent here. And finally, I'd like to introduce one more key feature in SmartJOI, the JOI pen. With JOI pen, users can customize a character's action, thought, and relationships to create a more personalized experience. Any customization made through JOI pen are inserted into every prompt as important notes, ensuring that task instruction prioritize this user-defined preference. So that's the SmartJOI pen. Let's see some example together here. If you type "you love exercise," you practice exercise every moment, then JOI choose the actions related to exercise, and what he say is pushing through this set, strength builds balance, keep it steady. Okay, cool. Another example says, if we type "you were supposed to die 10 years ago, but something kept you alive," then the JOI say, "Even fate couldn't dim my light. The paper reminds me I'm still here, alive and striving." It reflects well. Okay, so through these slides, I have explained all the agents in our system. Then we need to verify our agent system with different size of language model. And to evaluate its performance, we focus on three key aspects. First one, functionality, ensuring that all agents operate correctly with the game and execute their intended task without failure in the game. And the second one is checking whether inner thought and diary generation align well with the given input information and the coherent and readable. That's the second one. And the last one was contextual behavior, which means verifying that when we customize JOI's personality and preferences using JOI pen, its action accurately reflect the intent. So we first tested out agent design using different size of language models. From this, we confirmed that large language model performed well, while small language models struggled with understanding instruction and context. For large language models, reasoning models like OpenAI O3 Mini improves alignment and coherence in responses compared to GPT-4o. That's the one point. And to obtain evaluation metrics, we prompted to GPT to evaluate multiple samples based on predefined evaluation criteria for each task. So we use GPT as an evaluator, not human, for this table. And we specifically evaluate how well the generated text align with character's background, state, and personality, including writing style and tone constancy. And the table presents the average score from these combined evaluations. And the third column indicates how well JOI's action over 2 hours reflected the JOI pen context. So ensuring alignment with provided information. Okay, so LLM performs strongly well, but small language models struggle to maintain accuracy and coherence, as we can see in the table. Okay, then let's compare an example generated by different models. When we look at O3 Mini and GPT-4o, we can see the blue text that aligns well with the character's personal background, which says having a strong curiosity and interest in everything in the world. However, Minitron case, in the case Minitron, without fine-tuning, the model fails to incorporate personal background. So instead, as seen in the red text, it sometimes echoes the task instructions rather than following them correctly. And when we use the JOI pen prompt to add context for exercising, JOI pen prompt was, "You have a fitness challenge tomorrow, so just focus on your fitness work." Then the large language model successfully incorporate the context to the action selection as shown in the blue text. However, in the case of Minitron, the context is not reflected, failing to adjust the behavior accordingly. And additionally, utility AI, which relies on predefined rule and scoring, cannot incorporate context at all, of course. So if we used a large language model, we could have deployed it directly. But as we discussed earlier, our goal was to run a small language model on device to eliminate operational costs from large language model inference. So additionally, in inZOI's 5x speed gameplay, maintaining fast action selection without noticeable delay was critical. So given our constraints, where the game had to handle graphics rendering alongside AI processing, we had only 1 GB memory available for small language model inference. And for smooth gameplay at 5x speed play, we need a throughput of 3 ZOI action selection per second to ensure there is no noticeable delay. Within these constraints, our goal was to achieve performance as close to as large language model as possible. As a result, we selected Minitron heartbeat size due to the constraint as 1 GB VRAM constraint as our small language model. And to achieve this, we need to distillation process, where we collected data from a large language model and fine-tune the small language model. Let's take a look at how we did this. And we simulated our designed large language model agent within the actual game environment and prepared a setup that allowed dataset collection without rendering. This enabled us efficiently generate a rollout dataset for distillation into the small language model. By disabling rendering, we leveraged a large number of cost-effective machines with low-performance GPUs, allowing us to scale up data collection efficiently while keeping costs minimal. And then we collected a data set consisting of input prompt and output pairs for each task. To obtain diverse data set, we simulate many different ZOIs in different personal backgrounds. And to optimize performance, we fine-tuned the small language model using data from reasoning model, which shows the best performance in our agent. And our goal was to train the small language model to generate output similar to large language model when given the same input prompt. This ensures comparable reasoning capabilities while significantly reduce computational cost. So let's see the third row. After fine-tuning the small language model, as shown in the table, the performance improved significantly, but it was still not as much as large language models. And one key observation from the small language model fine-tuning was that while large language models require highly detailed instructions, as I said before, to generate high-quality data, however, once we collected the data, we found that small language model could still learn to generate similar outputs even without detailed instruction in the input. As we can see in the example, we removed most of the detailed instruction and kept only 1 or 2 special tokens to distinguish tasks. After fine-tuning, the model was still able to correctly differentiate tasks, and its performance remained almost the same compared to the model fine-tuned with the full instructions. So, however, this approach significantly improved throughput by about 30%, making it much more efficient. So, next slide, we will discuss how we integrate our small language model agent on device using NVIDIA's in-game inferencing SDK and Evgeny will give the talk about this.
Thank you. So before getting into too much details regarding our SDK, let's take a small step back and see what actually we have in our hands while we are about to start running this model within our game. So to summarize, we have a small language model called Mistral NEMA Minitron 0.b, and we have a performance target defined, which is 3060 and everything above with 8 gigabytes of memory or more. We take our model, we did all the fine-tuning required to get the predicted output from the model based on our tasks. We can also, this is currently work in progress, we still have this single model, but we are also trying to utilize it in a best possible way, and for that, we may use low-rank adaptation where we share the single model weights almost for everything, but then have very specific tuning to fulfill specific tasks when there is not enough flexibility in the current setup. And also we can use grammar-based rules for generating the output data just to drive it in a better way so it will work again better for our needs. Again, we're using the network and the model with the instruct mode, which indicates that the context is not persistent. So we just throw the prompt, get an output, and that's it. We don't need to keep any live state. And this actually helps us in a lot of ways just to be more flexible with every kind of task you can imagine. But what are the problems you'll probably face once you start experimenting with like local inference? If you're familiar like with Linux and data centers, it all looks nice for AI. You have very specific models to run. You have unified architecture, like the same racks all around, and you can just run whatever is needed with no issues. But with games and Windows, the story is a bit different. There are many frameworks nowadays, including the same like data center-based TensorRT. You can have Onyx runtime with Windows ML. You can just directly use DirectML. Or we have other frameworks like Llama CPP or Whisper CPP to run GGML locally. And nowadays, we may even have a path to run local inference within HLSL with cooperative vectors extension. And for our task, we specifically choose Llama CPP and GGML to run our language model. And for that, we're actually not using these frameworks directly. So our idea is to be able to present you an SDK which can be utilized directly to start your experiments with local inferencing. And this is what you will get if you will go to our developer site. So you will understand that NVIDIA and Game Inferences SDK is something that's supposed to help you with running local inference with high efficiency, and the benefits will be scalable model support. You can have different models. You have simplified deployment, and we also take care of performance as much as we can. But the really important part here is that you can already go there and download. So it's a live product. You can start working with it right now. But to understand it better, let's take a look at high-level goals we had in mind while developing this SDK. First of all, we just want to promote AI and simplify adoption for local inferencing. And for that, we designed a pretty flexible system, which is all plugin-based. The idea is that you wouldn't be driven by some monolithic concept of our SDK. So you may choose individual plugins. You may even customize them by yourself, so which also means we will be releasing the source code. So you'll have whole plugin access. You may customize it and even ship it with your custom version of a plugin. And it's all supposed to work with the same in-game inference SDK umbrella. We try to optimize the scheduling part, and also we apart from just local inferencing, we also try to support you with running your tasks in a cloud. So at a glance, the whole SDK is structured in a way that there is very thin core API, and the rest are just plugins. So it provides you different models to run locally and in the cloud, and it's sharing various models, some like NVIDIA-specific models, some models which could be found just in the internet and easily downloaded. For our approach, we specifically choose to run on GGML, and we use our specifically trained model called Minitron 0.5b. And currently, the inference is supposed to be run with CUDA. But I think at this point, we are already good enough with shipping additional support to run it on different configurations, including other vendors with Vulkan extensions. So it's not limited by CUDA anyhow. It's just our initial release was targeting these specific targets to make sure everything runs and tested well, but we're going to extend it through the time. To understand a little bit better what plugin and model is, so plugin is basically just a framework and container to run your model, and the model is the actual algorithm. So it represents the whole core flow for the algorithm, including some extra steps for pre-processing and post-processing the data. And we may have a single model per plugin, or we may have multiple models if they're compatible. So the way it works is your game connects to IGE core, and then you choose a specific plugin, and then you can have a choice of local models to run based on the current hardware capabilities, and you can load one model or then unload it and choose another model if needed. But this is not just it. So we also have this thought that it would be nice to support you with additional cloud services, and through our IGE plugin, which is called GPT-Cloud.rest, you can actually load various models from the cloud, and you can run inference in cloud. And it's not just the models. We try to give you access to our NIMS services, which is NIM stands for NVIDIA Inference Microservices. So these are like dedicated containers to run specific tasks directly in the cloud. And also we are giving you access to cloud service providers which run, so many of them run OpenAI API, and you can use directly that through IGE. And again, this is not the final state. We're also trying to support developers and users by giving access to GeForce Now inference service. So the idea is that you can use GeForce Now infrastructure and run inference in the cloud. So the user may have a subscription for GeForce Now, and this subscription can also be used to run inference tasks. Because again, the inference tasks are not free when you're running something in the cloud. Somebody is paying for it. And it's not a trivial problem to solve, and we try to support both developers and users the best we can here. Again, we design our API like local inference and cloud inference in a similar way, so it's not exactly the same API to connect to the cloud, but it's very consistent, and so there are very minimal changes required to have access. Let's talk about performance. When we do inference locally, we still care about frames per second, because this is what user feels. If frames per second do not look good, you have stuttering, then you have a problem to get fixed. But even though the frame rate may be good, and you feel like there is a fluidity in your game and doesn't crash, it's not the whole story. Because with running local inference, you have to take additional factors into account, and one is latency. We design our pipeline in a way that we run dedicated AI tasks in parallel with graphics. And although we try to schedule it in a way that the side effect for the graphics will be minimized, it all increases the latency of your AI tasks. And for that, we need to guarantee that specific tasks being run for AI pipeline, they are controlled in terms of latency. We need additional tools to measure this thing within our pipeline. So if you run any tests locally, you should pay attention not just to FPS numbers, but to the latency as well. And you probably need to craft dedicated tools to support it within your game. It's really important to understand how it works and what problems you may face with, let's say, we have multiple agents. What will happen if they all need AI-driven response right here, right now? How are we going to handle it? And that's why we always need to maintain this tricky balance between like FPS latency and also the memory footprint, because nothing is free. So the model lives on GPU, it takes memory. We also need some additional memory for the caches. So it's all needed to be taken into account. The good thing is that we try to support you on various fronts, and one important thing within in-game inference SDK is how we run CUDA nowadays with graphics. Historically, it was not a simple path, and there were lots of things to take into account with just running CUDA, because it's like a separate workflow, separate context from graphics, and if you just natively run it, there will be a lot of interference between two. The context will switch back and forth, and you will have a lot of degradation in terms of performance. So your FPS will degrade, the latency will be high. And the idea we solved it is that we introduced this concept as CUDA in graphics, where we actually execute CUDA context within the graphics context. And this almost eliminates all the issues. And you can run your graphics as previously, and CUDA no longer takes its individual context. It's all run within the same thing. And the benefits are that you can more efficiently utilize your GPU. You can run CUDA when graphics is idle. You can run graphics when CUDA doesn't give you any extra workloads. And you can improve both on your execution speeds and latency. And of course, it's really important to notice that we need extra tools to monitor this. And for that, we actually just recently released a few updates, both for our Inside system and Inside graphics. So now with Inside graphics, you can inspect both your graphics workloads as well as CUDA workloads, how everything is being run on the GPU. And I think that's pretty much it for today. It's just worth noting that although the game will be released soon, I think we're still not done with improving on various fronts, with making more complex decisions and flows to make your game experience more advanced. We're still doing a lot of experiments and optimizations on our side. So you can expect a lot of updates. So I think it's relevant to say that we're just started with this AI thing, and we'll be happy to answer any of your questions right now. Yeah, please go to the microphone.
Hi, I'm Evan Dong from Tencent, and I have two questions. About first of all, what you did is fantastic. I love the ideas and what you did in the inZOI. My first question is that I noticed that in the showcase 2 years ago, from the inZOI, that you're trying to introduce the inZOI memory and more deep interactions between the inZOIs. I would like to know if the memory is introduced in the inZOI game, what will be like about the total small language model? It will affect the appearance. What is the challenges if the memory is introduced in the game?
So you're specifically interested in challenges between
the challenges and the memories will what kind of the differences will the experiences will be affected by the memories and the technologies.
Okay. Do you remember? Because I'm probably not aware of the prior context.
Yeah,
that was presented.
I think in the inZOI showcase 2 years ago, the roadmap of the product is you will introduce the NPC memory in the game. right? And I would like to know if the memory is introduced to the game, what the challenges about a very small language model?
Yeah, I think so currently everything is structured in a way that you pack everything in a single prompt.
Yeah.
And you can just add whatever works with your like fine-tuned model. To give more context here, like the prompt size is currently limited to several thousands of tokens.
Yeah.
And whatever you can fit there should work. So you of course you need fine-tuning to make sure that all various factors will be taken into account. But basically the restriction nowadays for running local inference is to be able to fit with this prompt budget.
Okay.
And it should just work. And another tricky thing here, I think it's just worth highlighting again. It's not even about being able to fit everything inside a single prompt. To be efficient, to run things with a high scalability at runtime, you need to be able to operate with as little like output tokens as possible, ideally just one. If you can just have a pretty sophisticated input and then get a single token back which will drive your gameplay, this is the way to go.
Yeah.
This way you'll just gain the best efficiency out of it. So this is what makes it performant and real time and scalability, gives scalability.
Okay.
But again, the memory, so whatever you can incorporate into your prompt and take into account, so yeah, it will work.
Okay, thank you. My second question is that I noticed that the inZOI recommended hardware requirements a little bit high, and it raised the entry barrier of other users can test this inZOI. So I would like to understand, is that because you put a small language model in the game, so it cannot lower in the future the requirements?
I wouldn't say we have very high requirements. Currently, it's 3060 and above to be able to run it locally.
Okay.
I think it's reasonable. We may try to improve. Just for initial release, we just want to make sure that we actually scale well, because for a single ZOI, for a family, it may work well, but if you have tens of them, and you need to generate like long inner thirds, you need to make sure that it will all scale well and you can actually handle it along with the graphics.
Okay.
Of course, we like on PC, it's pretty common just to play with your local settings, and if you can degrade like your visuals in favor of inference, it's still an option probably at some point for those who would like to have this immersive gameplay, but maybe sacrifice visuals a bit. And this way we can probably allow it to run like on the previous generation of hardware, but still we feel like the current requirements are reasonable. But it's just for initial release. We'll try to do the best we can in future.
Okay, thank you.
Thank you.
Hey guys, really cool talk. Helps to show how AI can get used in the future in simulation games like this. I am a designer and worked on Paradox on Life by You, which was their sim-like game. And we experimented a little bit with something similar to this and ultimately decided not to use it for various reasons. But one of the reasons was all of the NPCs wound up feeling very similar to each other. So I'm curious, especially in the experiment you just showed, there wasn't a lot of personalization between those two characters and their inner thoughts. So yeah, I'm just curious if you feel like you can kind of get the personalization of each individual agent out of the large language model.
Okay, just to summarize, so the question was about personalization, how we can control that, and yeah, for that, it can be tweaked. Yes, please. Let's hear the developers.
Okay.
Okay. For large language model, they usually follow the instruction well, so they gave it a different personality well. But for small language model, if we fine-tune the model, that diversity is decreased, as you said. But to address this issue, we use various different large language models. For example, using Cloud, GPT-4, or Grow. So we can make a diverse type of language model. We can use diverse type of language model to generate diverse data set. First thing is collecting diverse data set. Then we try to fine tune the model with the huge size of the data set. Then we observe that the different personality is getting better when we try to fine tune with the huge scale of the data set. So we are trying to collect more data set.
Interesting. So you actually used multiple models to collect the wider set. Interesting. Cool.
Yeah.
All right. Thank you.
Hey, thanks for the great talk. It was incredible. I'm working on a live sim, MMO live sim called Seed. So like, it's really cool to see that you're solving all the problems we're also kind of solving. I have many questions, but I'll just go with like one or two, which is your decision making is all like very agent centric, right? So it's just one agent picking a decision for themselves based on how they're feeling like internally or their context. How does this translate to multi-agent coordination? So for example, like in that example, the husband is hungry, but the wife is not. So then like what kind of, like do they generate interesting coordinated actions?
Thank you. So the question is how different ZOIs may affect one another based on their like individual decisions, how we're gonna control it. I guess this is something to consider for the future work. So we are basically just started with it to give your like more immersive gameplay with just this more human-like behavior where various factors are taken into account, and it's not an easy task. Sometimes you face a stranger and you may not even, although you're both humans, you may not interpret his behavior correctly. You may not understand the whole context. But at some point, we will try to do the best. There are lots of internal ideas in the studio to improve on the current state and to try different things where you'll just use the smart ZOI pen just to directly affect the current state, just to override it if needed. But this is something that can be already taken into account by just adding this extra input from one ZOI to another ZOI's prompt. But we just need to make sure this is well tested and probably tuned better for this type of communication. But
Okay.
Thank you.
Thank you. Just one more question. Like, are you also seeing very coherent behavior across time? Because like the beginning, it's nice, but like also do you see it like coherent behavior that makes sense throughout the day?
It's all well controlled. So it's all controlled with how you design your prompt. So it will not degrade over time. But I guess the idea is that over time you would like to incorporate more data from all your previous actions being taken, so it will like feel better based on your previous experience. But
okay, so as long as you keep your memories and everything kind of like limited and you don't keep increasing it. All right.
Sorry, we are running out of time, but we're still here to listen to all other questions.
Yeah, thank you.
So feel free just to come here and discuss.